Hello everyone, my name is Gopakumar. I am from the Department of Chemistry and I am a physical chemist, and my speciality is surfaces and interfaces, and we look at the surfaces and interfaces using different type of microscopy and spectroscopic technique. So, in this course chemistry and physics of surfaces and interfaces, what I would like to bring to you is a flavor of the chemical aspect and the physical aspects of surfaces and interfaces. So, before going into the chemical and physical aspects of the course, we would look at the importance and the interesting aspect about the surfaces and interface, and that is what going to be the content of lecture 1, in which I will show you that why surfaces and interfaces are so interesting, or is there something important that we need to take into account about surfaces and interfaces. And you will also find out that during the course of the lecture that surfaces and interfaces are one of the most important ingredient in modern technology, particularly the thin film based technology. So, in lecture 1 we will have a look at these important aspects about the surfaces and interfaces. So, the first point is that surfaces and interfaces are present everywhere. So, when I hold my hand onto this table, or when you touch a surface, when we actually interact with the air, or when you move around, everywhere there is actually a surface that is interacting with another surface. So, that means you cannot avoid surfaces and interfaces at any course of time while you are doing anything. So, if you would look at the examples like solid vacuum interfaces, where an object is actually kept inside vacuum, this is actually one of the most idealistic interface, because the solid can actually be understood just not interacting with anything, but that is actually the most idealistic case. But when you come to normal life, that everywhere there is actually an interface. For example, here you have a solid liquid interface where water is passing through rocks, which is basically a solid liquid interface, or you have solid interface whenever you encounter object on another object. So, what I would like to bring to your point is actually that surfaces and interfaces are present everywhere and we cannot avoid that. So, of course, the vast area of surface and interfaces will not be covered in this course, but we will be looking at the most chemical and physical aspects at a molecular level, so that one can actually understand these surfaces and interfaces in a more quantitative way. So, why surfaces are so interesting? So, we need to first address that question before we go into the bulk of the lecture. So, first of all, the main aspect that you would be just telling is that, well, since we are always in touch with another medium, or when you do anything you are basically just coming in contact with another surface. So, therefore, interfaces are ubiquitous. So, it is always present. So, then of course, it is obvious and clear that we need to clearly take into account about interfaces. But let us look at a few specific examples to understand this in a more quantitative or in a more interesting way, or the interesting aspect about the surfaces and interfaces. So, this is a lotus leaf, and lotus leaves or colocasia leaves, for example, are very popular for having their non-sticky property. So, that means if you drop water on the top of these leaves, they will never actually stick onto the surface. Or so, we will look into the technical details of that. Why is this happening? Is there something interesting at this surface that makes actually the so called lotus liquid interface kind of interesting? Then let us take another example of a gecko moving on a vertical wall or on the rooftop, which never falls. Yeah, so this is also an interesting interface that you actually create between the legs of the gecko and the solid. So, it is a solid-solid interface. So, what actually causes this gecko not falling off the window is actually a question that one can actually just address by looking at what happens at the interface of this gecko and solid. Or for example, plant leaves. So, they are actually very beautiful in looking, and just at the macroscopic level of the leaf you would not be able to clearly recognize or understand what actually is going on, or why or what is the microscopic structure of the leaf itself. So, what I am going to now address is basically to look at the microscopic picture of these three objects that we have talked about. Well, I have already told you surfaces and interfaces are ubiquitous, you cannot avoid them, but what is interesting is actually just to take these examples and to look at the microscopic level and see why this interface is so special, or why the surfaces are so special. So, let us look first the lotus leaf. So, when you look at the scanning electron micrograph of these lotus leaves, so what you can see here are extremely tiny objects. You can look at the scale of the image is about 10 micrometer, and that actually tells you that what you are looking is actually in the microscopic regime, and you can see like tiny nanostructures are protruding out of the surface. Although the surface look very smooth at the macroscopic level, when you look into the microscopic level, you notice that there is basically very fine and interesting nanostructures. And now, if you look at the scale of these nanostructures, they are typically in the order of a few hundreds of nanometer big. Now, the point is, when a water molecule want to drop and want to stick onto the surface, and if there are these tiny nano objects which are present on the surface, then the water is basically unable, or the water droplet is actually unable to come in contact directly with the surface of the leaf. So, the nanostructure or the topography, the special nanostructure or the nano microscopic structure on the surface of lotus leaf actually reduces water being in touch with the surface. So, nature actually does this interesting game with surfaces in order to achieve a certain important outcome. So, that is actually the so called hydrophobic nature of water on the lotus plant. Of course, it is also the material that is important, but here what we look at is the type of surface that actually causes the real non-sticky nature of water onto lotus plant. Now, if you look at the gecko feet, for example, and the gecko feet is also been looked using microscope, and this is actually scanning electron microscope, where you can see tiny spatula like objects which are actually present if you look in a extremely smaller scale. So, this you can see here is about 100 nanometer, and at the 100 nanometer scale you can see there are extremely tiny features like spatulas. And the interesting thing what gecko does is actually using these nano objects, the number of contacts between the gecko feet and the surface is basically increased. Therefore, the gecko is basically able to stick its feet to the wall. Yeah. So, this is actually an interesting engineering that nature does using surfaces in order to basically achieve a certain goal, and in this case is basically that the gecko is able to stick to the wall without falling. Now, if you look at the plant leaves, so this is a particular example I have chosen. This is not very specific to a given plant, and if you look at any plant, you mostly would see that the surface of the leaf is always having these kind of small nanostructures which are present on the surface. And of course, at the end what it looks like that in the microscopic level the surface is not anymore smooth, it is much more rougher than what you actually just see at the macroscopic level. So, it actually is interesting now, the nature does this thing in order to increase the efficiency of the photosynthetic process. You have to actually absorb a lot of carbon dioxide and water in order to do the photosynthetic process, and therefore, the surface is actually kept extremely rough so that to increase the surface area. and by doing this nature basically achieve a large surface area, and therefore the efficiency of the process increases. So you see what in this particular example what we have focused is that by looking at the microscopic level and looking at the microscopic nature of each surfaces, one can basically understand a lot of interesting aspects which you would not be able to address at the macroscopic level. Now let us look at a certain example of at the molecular and atomic level. So this is actually a gold crystal, a gold 111 crystal. So later in the lecture you will find out what is the meaning of this 111, and this 111 are nothing but the HKL index or the Miller index. We will actually just look that in greater detail later. So this what you are seeing is a crystalline gold surface, and what you see here is actually the gold atoms are well connected by a hexagon. That means the idealized crystal structure of gold 111 surface should basically look like a 6-fold symmetric surface. Or if you look at the diamond structure, it also appears to be extremely crystalline, and in that also the diamond or the top surface atom is basically the light blue one, and they are also connected and forming a perfect hexagonal lattice arrangement of the surface atoms. But now the interesting thing is that this is basically the expected atomic level arrangement of the gold crystal and also the diamond crystal. But what is very interesting is that if you look at the real gold surface or the real silicon surface using microscopy, what you see is something absolutely weird and different. So that what you are seeing here is actually an STM, which is scanning tunneling micrograph. We will actually just address this later, how you obtain this image. So this is a scanning tunneling micrograph, and what you are seeing here, these bright lines are nothing but the arrangement of atoms, or it is basically an atomic lattice. So as expected, here you would have expected to see basically a 3-fold symmetric arrangement of the atoms, but instead in the real microscopic structure or the real microscopic image of a gold 111 crystal looks entirely different. Why is that? It is actually due to the fact that no surface is actually stable, and therefore it undergoes something called a reconstruction, and due to the reconstruction the atom on the surface is actually rearranging and forming an extremely different pattern, which is known as a herringbone pattern. Or if you look at the silicon 111 surface, as expected you would have seen basically a hexagon, but instead what you are seeing is a much larger hexagon, but the arrangement of the atoms are looking entirely different than in the expectation. It is also due to the fact that the atoms on the surface actually undergo a rearrangement due to something called as reconstruction, and the surface is actually then giving rise to something like an entirely different microscopic structure than what is expected. So what you see here is actually again at the microscopic level you see that there is a huge difference in the way the atoms are arranged on the surface. So you would ask a question at this point whether it is important to know the surface if I want to basically do something with the surface. Yes, it is important that one need to know clearly the microscopic structure of the surface in order to basically use the surface. Yeah, because this was actually the expectation, and the real outcome is somehow very different. So that is also the reason why in our course we will also be looking at these particular surfaces or even more surfaces using microscopy in order to clearly understand the microscopic nature of the surface. So the next most important aspect of thin film I would like to bring to your attention is its application in thin film technology. For example, in most of the modern devices that we use, for example in diodes, thin film transistors, solar cells or whatsoever, we would be using basically a technology that is based on thin films. That would means if you would like to construct a light emitting diode, we would need to basically use the thin film technology, and we need to basically understand the underlying basic principle of interfaces. To understand that, I have here a basic construction of a light emitting diodes, and as you see here, they are constructed by many different layers. It has already 1, 2, 3, 4, 5, 6 layers of materials are put together, in which the most important is basically the layer number 3, which is the emitting layer, and where of course the light is emitted when you apply a load or when you apply an electrical field. But in a simple light emitting diodes, what you would require is only 2 electrodes and an emitting layer. But in modern light emitting diodes or a more efficient light emitting diodes, what you need are these additional layers like 2, 4, which are nothing but the electron transport layer or the hole transport layer. Well, what are these? These are actually the layers that brings electrons and hole to the emitting layer so that the recombination is more efficient, and therefore you get basically a higher efficiency in the light emission from the light emitting diode. So you can basically see that if I need to construct this kind of a light emitting diode, I need to basically understand what is going on all these interfaces. So I am basically constructing already 6 or more interfaces already in this very simple device. That means if I need to clearly understand or make this device work better, I need to clearly understand what is going on at these interfaces and what sort of chemical changes or what sort of electronic property changes or what sort of microscopic property changes are happening at this interface is a most important ingredient in constructing such devices. Therefore, for us, the interfaces are the most important. As you see, we have already 7 interfaces here, and we need to basically understand all these interfaces at its microscopic level, at its chemical level, and also at its electronic level in a highly detailed way. And you see that for a simple light emitting diode or a simple electronic device, we are already coming across with many such interfaces. And that is the importance of understanding the interfaces in general and when it comes to the technology. I would also like to bring to your attention that there are already exciting news when it comes to the chemists, because there are already examples of organic light emitting based TV. You already have it in the market, the flat TV and the curved TV, which are basically using the organic light emitting diodes, in which the so-called emitting layer is basically nothing but an organic molecule. So this would be an organic molecule. Yeah, organic molecule. So this is a good news for chemists. So we are basically now also going on with modern technology where we would be using basically also organic layer. Well, at the end of the day, what I would like to demonstrate here in this slide is that what we are basically just trying to do is actually using the thin film technology in constructing our modern devices. Therefore, it becomes a must in understanding the interface, chemical, microscopic, and electronic properties. Now I would like to show a few more examples of application of thin film in technology, particularly in electronics. So this is one foremost example. That's actually a field effect transistor. And field effect transistor is in fact the most important and the fundamental building block of all electronic devices. You name a computer, you name a phone or display, whatever electronic device you take, you will always come across a field effect transistor. Now in this type of a field effect transistor, this is particularly an N-type metal oxide semiconductor field effect transistor, or generally known as a MOSFET transistor, in which you have basically an N-type material here and a P-type material here, which is making an interface. And now, as you already see, this is an interface. This is another interface which makes this typical PN junctions. That is actually the fundamental units of this particular device. And now each of these N-type semiconductor material is actually again making an interface with metal, which is nothing but the drain and the source of this device. Then the p-type material is actually making an interface with an oxide material, and again the oxide is making another interface with the gate electrode and so on. Yeah? And then finally, even the p-type material is actually making another interface with the body ground. So now you already see that in this very simple device, and the most important device indeed, you have about 1, 2, 3, 4, 5, 6, 7 interfaces are already included in this very simple device. So that means when you want to basically just get this kind of devices operational or functional in an efficient way, it is quite important for us to understand these interfaces. And without understanding the interfaces, you cannot construct them in an efficient way. So therefore, from the technological point of view, studying interfaces or making interfaces are quite crucial in the development of modern technology. And that also gives a great perspective for us to study actually the interfaces. Let me also show you one more interesting example, which is actually the fundamental principle that goes under the hard drive disk or any sort of this kind of disk where you store basically information. This basically uses the principle of giant magnetoresistance, and for the discovery of the giant magnetoresistance, Albert Fert and Peter Grunberg has won the Nobel Prize in 2007 in physics. And what it actually uses is again an interface of a few different materials. So here you have a ferromagnetic material making an interface with a non-magnetic material, and again with a ferromagnetic material. Now you create this nice interface of the materials, and now imagine that both the ferromagnetic materials are actually having the same orientation of their magnetization. Both are up orientation. Now, when the electrons with the spin specific electrons are passing through this material, you can see if the spin of the electron is matching with the magnetization of the material, so like here in this case both up, then the electron is basically able to transfer or transport through the material without any resistance. But the moment the spin of the incoming electron or transporting electron is basically opposite to that of the magnetization of the material, the ferromagnetic material, then you see there is a large scattering that happens at all these interfaces, and then effectively the transport is very weak in that case. Well, by looking at or orienting the spin in the right way, we can basically use this combination of ferromagnetic, non-magnetic and ferromagnetic material. That means this particular interface or the combination of this interface in selectively transporting a type of spin. That means you can basically get the so-called the current with a specificity in the spin. So that is actually nothing but the spin selected current, for example. So that is the fundamental principle that you use in all this hard disk, and that is actually nothing but known as the giant magnetoresistance. And here also you can see a different combination you can use if you have like the opposite magnetization for one material and the other has the opposite orientation. Then you see basically the spin transport is facilitated at one interface, but at the other interface it is actually kind of scattering. Again, the same here. On one interface it is facilitated, but on the other interfaces it is basically not working. So you see, by again this kind of a device is again working using the principle of creating interfaces, so thin film technology. So ideally all these kind of magnetic hard disk devices are also using nothing but the thin film technology. Well, I would also like to bring one more example, which is nothing but a solar cell. And a solar cell is nothing but the opposite of the light emitting diode that you have seen. Here, what you basically do is you shine the device. Photon is basically just going through the material, and you have basically something like a light absorber. And the light absorber basically would absorb the light, and then you can basically split the hole and the electron, and then you can use that hole and electron to operate some electronic device. So this is nothing but the opposite of an LED. But you also see here that this device is again created by several interfaces that you put together. You have a contact layer, and then you have an anti-reflection coating layer, you have transparent electrode, you have junctions that connect basically the light absorber, then again contact, and so on. So you already see there are 6 or more interfaces here that basically connect everything together, and this is again the fundamental principle of an electronic devices. Yeah, so this is basically what I would like to show you, that the electronic devices are all using nothing but the thin film technology. So just to put it in summary, what I would like to bring here is that surface and interfaces, as you have seen, it is very crucial in current days technology, which is a thin film based technology. And in that, the microscopic structure of the surface basically controls the growth of thin films, because if the thin film need to be prepared, you always need a surface, and depending on the microscopic structure of this surface, you would basically be able to control the growth of thin films. Then the chemical interaction, so that is also something we are going to address a little later, which is actually coming to do with the chemisorptions and physisorptions and things like that. So the chemical interactions at the interface also controls the electronic property, for example. So you would actually just see later that depending on the interfaces that you form, you can highly tune the electronic properties. Then another interesting aspect, which is actually the charge transfer at interfaces. So what is a charge transfer? So now let us assume that you are creating an interface using a metal. So this is a metal and a semiconductor. So for a semiconductor, I have basically a band gap, which is like, therefore I have the valence band and the conduction band, and here I have the valence band and the conduction band, and this is basically my Fermi energy, and here in the semiconductor region I have an energy gap. So now you see that when you create such an interface, it is clear that this interface is very ideal. You can see that there is no change in the band structure of the semiconductor when it touch actually the metal, but this is very unideal case. So this is only a very ideal case where the interface electronic property remain as you would expect in the ideal case. But in a real case, what happens is the following. In the real case, what happens is that you have the metal and the semiconductor band start to bend near the interface. Yeah. So this is quite interesting, that this change in the band structure, which is typically known as band bending, is actually something to do with how the charge transfer occurs at the interfacial region. That means when an interface is formed between two different material, let us say like metal 1 and semiconductor, and then you can actually have a charge transfer, the electron transfer from the metal to the semiconductor, or you can have a charge transfer from the semiconductor to the metal. So depending on the charge transfer, you would basically be seeing two different type of band bending, either a downward bending, or you would also be able to see something called an upward band bending, and this would look like this. And this different type of band bending will have a strong influence on the electronic property of the surface and the interface. So therefore it is quite important for us to kind of understand how the electronic property of the interface is actually controlled by the charge transfer, the chemical interactions, and also the microscopic structure. So therefore understanding the physics and chemistry of surfaces and interfaces are very crucial in developing the new technology, which is basically based on thin film technology. Now I would also like to just show you a few daily examples that you also come across where you are using interfaces. For example, surface coating. So you are of course using something called paint every day in your life, which is basically to protect your surfaces, or for example plating, and this has also been used regularly for protecting surfaces, and also like to protect surface against corrosions and things like that. So therefore these kind of surface coating is also nothing but a formation of a kind of interface on different surfaces. So the physical and chemical properties of these interfaces is basically just defined by the texture and the composition. So, what is the texture or what is the composition of the material that you put onto the surface is actually defining the physical and chemical properties of these kind of interfaces that you use in paint, platings and etc. So, here I just took actually two examples from the market. This is actually two different type of paints that you are using in your daily life when you want to protect surfaces like walls or like metallic surfaces or wood and so on. And you basically see there are they come with this kind of advertisement called as Teflon surface protector, weather coat and so on. So, what you do ideally in all these things are nothing but just creating interfaces using different type of materials that will actually just help us in protecting the surfaces. Then for example, mirror is actually a best example of having an interface. The silver coating which you use to observe your image is basically a typical mirror, or you also can use actually like the thin film coating to have like a two-way mirror where you can actually observe the image on this side and also on the other side. So, this is nothing but just using different type of materials, and also like this modern sunglasses, windows and lenses that are also now currently available in market, where they use actually anti-reflect coating. So, this is an example of like a sunglass and a window shield, which is actually a sunglass and a window shield which is created using anti-reflex coating, and the outcome is very obvious here. So, like as soon as you use the anti-reflex coating, you can see there is no reflection in this sunglass, and also you can see here there is absolutely no reflection of the light of the opposite approaching cars, and therefore like your visibility is very nice in the night. So, this is the type of different interfaces that you would come across in your daily life, and which is also kind of commercially available. Well, as I told you, surfaces and interfaces are ubiquitous, and in this lecture what I could conclude or what I could show you is that different possible aspects of surfaces and interfaces, and actually their presence in nature and their presence in technology, and also their presence in daily life and so on. With this, I would like to conclude the first lecture, and I will now come to the second lecture, and in that I will just give you a little bit of the historic perspective of the surfaces and interfaces and the development of surface science itself. Thank you very much.